Hi and welcome to Ultrasonic. In this episode we're going to build an ultrasonic rangefinder using Arduino, a HC SR04 or SR04 ultrasonic sensor and a small OLED display. We're also going to look at the problem you can encounter with these sensors which can catch you out if you're not careful, particularly perhaps when you're developing your project. Let's get started. Is that it? So let's look at the circuit diagram and the actual circuit on the breadboard. I'll just pull out the sensor so we can see the power connections more clearly. The Arduino connects its 5V pin to the red 5V rail here, going under where the ultrasonic sensor was. In the same way, the ground connects to the blue ground rail, going under the sensor again. So both these top rails are now connected to power and ground from the Arduino. For the OLED, we connected to required power and ground here and here to the top rails. It's an I2C device using an SSD 1306 driver. The SEK, which is the clock, connects with the yellow wire to the connection marked as A5 on the Nano. The SDA connects with the blue wire to the connection marked as the A4 on the Nano. If you want any details on setting this little screen up, or these little OLED screens up, then see this link. I'll put it up there right now. Let's look at the sensor. You can see when I put it into the board, the power and ground will connect here at this end and the other. Let's push it. Let's push it back in and see if we can connect it to the two middle pins with this yellow and blue wire. The pin marked. What is it, Doug? I'm busy recording. Well, you don't think it'd be a good idea to quickly go over the details of getting the OLED up and running in this video rather than them clicking a linky thing and shooting off to another video in the middle of watching this one and then trying to come back and just saying. Okay. I'll go through the software setup for the screen as well here. Just get off the screen, okay? Okay. You know it makes sense. Whatever, just bugger off. Right. Where were we? Oh yeah. The ultrasonic sensor. Right. The pin marked trigger, which is this one, connects using this yellow wire to the D12 pin of the Nano, just coming down there. And the pin marked as echo, just next to it, connects with this blue wire to the D11 pin of the Nano. And that's it. It really is simple to make a self-contained range sensor. Obviously, you need to mount it in a box and mount all the parts on some sort of perf or strip board to make it into a better project, but from a hardware point of view, that is it. As mentioned at the start, there is a trap with these ultrasonic set units, but more about that later. Let's move on to the software. So, we'll install all the required libraries first, and then add in the very basic software to measure and display the distance on screen. First, we'll install the ultrasonic library. Go to your libraries manager and type in new ping into the search bar. Install this library here. Don't forget the display libraries and setup. Yes, I hadn't forgotten it. I was just going to do it now, and now you've actually stopped me from doing it. I mean, what is the point of me trying to do it if you keep interrupting and then stop me from actually doing it? I mean, what is the point? Okay, chillax, Extronical. Go. Just go. Okay, where were we? Next for the display. Again, go to the library manager, type in Adafruit 1306. Install this library here. Then type in Adafruit Graphics. And install this library here. Close the library manager down, and then the code to drive this is on the Extronical website. Let's go there. Under Basics, Environmental, ultrasound rangefinder, copy this code into your Arduino IDE and upload to your board. Quick test. Cool, works fine. If yours isn't working quite correctly, displaying incorrect distances or something similar, then stick around till after the explanation of how it works, and I'll replicate that problem for you and explain what's going on and how we can fix that. So how does this all work? In a nutshell, they emit a high frequency sound pulse, i.e. ultrasound is above the range of human hearing, and then listen for an echo of that sound coming back. Let's use a diagram. Here's our rangefinder and here's a wall. With our Arduino, we can tell the sensor to emit a pulse, and at the same time we start a timer in the Arduino and monitor the echo pin for changing. The sound pulse moves off, is reflected by the wall and echo, and returns eventually to the sensor. When the sensor detects this, it triggers the echo pin. The Arduino then stops its timer. Now, to work out the distance, we can use the equation distance equals speed multiplied by time. We know the time it took for the pulse to go there and back as we measured it with the Arduino. And we want to find out the distance, but we need the other parameter, speed. How do we get the speed? The speed of an ultrasonic wave, sound wave. Well, the speed of sound is known, well, sort of. The speed of sound, or the speed of that pulse, the speed that the sound pulse travels at, depends on the density of the air that it's travelling in, which of course can vary slightly on a day-to-day basis, but on average it's around about 330 meters per second. So now we know the speed and the time, it's then a simple matter of doing the above calculation. But hold on, we've just calculated the distance to the wall and back, which will be twice the distance we want. So we would then just simply, to solve that, divide it by 2, and that would give you the distance to the wall. And that's all the Nooping library does. It works out all this for you, and you just use a nice simple function call. Let's have a quick look at the code that we've just put into our Arduino. You can see the function we call here. There is a similar one to get it in feet or yards or whatever you want to work on, as well as this meters and centimeters. And using the graphic library calls here, we display that result on screen. Let's move on to testing and look at the actual problems you can have if what we've talked about if you're not careful. So here we have our sensor all ready to plug in. We've got a tape measure to check how accurate it is, and it's point at a nicely new plastered wall, a nice new hard surface. And we have our tape measure running back along the table, and we can see how it is accurate over that distance. So let's plug it in. Apologies for the light level. You're going to get some shadows and things, and I've not got my normal light because it broke, just to try and help the low light situation sometimes in this room. But we'll see how we get on. So I'm plugging it in. 30 centimetres, and yes, it's more or less there, isn't it? About 30 centimetres, 30 and a tiny bit. That's quite reasonable. So let's pan it back and we'll see how accurate it is. So let's move it to 50, which is there, and bring that up to the 50 mark. 51. I still think that's quite reasonable. It is slightly over 50 if we move it to exactly 50. Yeah, but it is. That's a centimetre out at that point. That's okay. That's fine. I'd be happy with that. Let's move it to... Oops, we moved the tape measure a little bit. Let's move it to 70. Let's see how it does at 70. Move that back a little bit. A little bit. And again, 71 centimetres. Okay, so we're about a centimetre over or so. Let's just see when it goes to 72. So yeah, you could actually alter the code a little bit. As I said, the speed of sound depends on the air density. The air is quite warm in this room, which means it's actually slightly less dense, so it would actually be travelling a little bit slower, so things can be a little bit inaccurate. So 72, let's try 80. So I'll move that to, oops, just catching a couple of things, move that to 80. And yeah, 80, 81, that's fine. Let's try 90. Make sure there's nothing quite catching its way to give a false result. So at 90, again, not too bad. 91 centimetres, just a centimetre over every time. Let's go to 100. Try and keep it pointing accurately. 100, we did have a bit of 102 is reasonable at this distance. I'd be really, but we're getting some odd lower readings as well. They jump quite dramatically lower down to the 80s there, and even a 94. Let's go to 110. Whoops, wasn't help when something drops right in the way. 111, not so bad, but we're getting these odd ones where it's dropping down a lot. Let's try 130. And we're at full stretch of the connected cable now. So we'll have a quick look what that reads. So we're getting some that are getting up to 130, but others are really low down. It seems to be losing its accuracy. And as a last test, I'm going to point it at my roof, which from where I'm stood will be around about nearly 2 metres away. So we'll do that. And from here my roof is probably about 1.7 metres, something like that. And we're not getting any result that closely resembles that at all. Let's repeat the test. Let's repeat the test with a battery pack. So we have just a normal battery pack. I'm going to connect that up, set it back to about 30 centimetres. And the actual sensors just popped out, just pop that back in. Let's plug it in. "30 centimetres seems reasonable. Let's move it to 50. 30 centimetres. Not anywhere near. Let's put my hand in front. 33 centimetres. Oh, we've got 5 centimetres, a bit slow, probably because of the averaging. Still saying 36 for 50. Let's move it to 70. Nowhere near. And all we've done is play, and this is a newly charged power pack. If we measure the current on these voltage on these little USB things, let's just pop that on. See what that's registering. So it's, as I say, it's got up 41, so a little bit nearer, but not quite near the 70 or nearly 71 that it is. Voltage is recorded there as 4.98, which is very reasonable. 4.99. But nowhere near. Let's replace this small silver cable with the one we had connected to the computer. See what we get there. So about 70. We've got improvement. It is definitely nearer. 58, nearly 60. Voltage is registering as 4.98-ish. Same as before. But yet we've got an improvement, although still fairly inaccurate. What this is leading me to believe is that there is a voltage drop over this cheap cable, which has never caused me any problems with any other project at all. But with this one, it is doing. And in fact, as we noted, over about 80 centimetres or so, even with the computer power in it, so the computer supplying the power over the other cable, we were getting distances that weren't recording accurate at all. And yet these devices are supposed to be good from about 2 centimetres to about 4 metres. That's what they're rated at. So the next thing to do is actually let's supply the power to this through a power supply that will keep a steady, well, when I say a steady 5 volts, what we're going to do, we're going to connect it to the voltage in on the nano, and then that will be regulated up through the regulator on the nano board to a precise 5 volts. Let's see what difference that makes. Right, so I connected up to my power pack to the voltage in, and common obviously, and I've set my power pack to my lab bench supply to 7 volts, which is about what they recommend when you're going in via the VIN pin to give a good steady 5 volts out of the regulator on the nano board. Let's switch on. And there we go, instantly an even more accurate result before. We're at about 70.5, it's saying 71, that is fantastic. So it's working really well. Let's try it at 80 where we start to get, we'll go to 90, start to get some flaky results. When we're connected up even to the computer one, which was better than the power pack, where we'd think we had a bit of voltage drop. It's at 90, or maybe just a tad over. So 90 and a bit, 91 centimetres, you can't argue with that, and that is steady at 91, where it was drifting in and out at 80s and what have you. So let's go to, say, 110. 112, you're really at that distance, I don't think. I mean, I've got a slight angle on it. Can't argue with that. 110, 111, 112. I'm completely happy with that. On the other one, on the computer one, which was the better, the power pack was useless at them sort of. The power pack was useless over about 30 centimetres. The computer was good up to about 80 or so, maybe 70. And this is showing a very good result at that. And all because we've gone 7 volts, using the 5 volt regulator on the nano board, so we've got a very steady 5 volts to this device. Let's go further back. Although we can go to, say, let's go to 130 and then we'll try the roof. As I said, the roof's about, from where I'm holding it, probably just less than 2 metres. Let's go to 1.3, 130 centimetres, and yeah, happy with that. 131, working perfectly. So let's try the roof. So I'm hoping though that the wires are going to pop out, so to try and point it at the roof. So if I hold it back there and point the camera up, so 1 second, I just need to loosen the camera so I can actually tilt it, and I'll point it at the wall. And then we'll have a look. We can get that on camera. Yeah, it's just less than 2 metres, so it's saying about 1.75 centimetres roughly. This is in line with the top of my camera-ish, 175 centimetres. I will double check that with this tape measure. Just have a quick check at roughly what it is. Let's do that. Just go to the ceiling and check what it is down to roughly that, the camera. And the guy at the camera is 172, maybe 173 from the roof. Again, over that distance, that is fine. So, lessons. Let's just tilt that back down there. Lesson to be learned from this. These devices are rated for officially, between 4.8 and 5 volts. But I'm not entirely sure what the voltage drop was over that cable. I was surprised it went below much 4.8. But they are incredibly inaccurate if they don't get exactly 5 volts. So we need a precise 5 volts to these. Anything less, and even a little bit less, and the results start to go more out, the more the distance goes. So basically you need to run it not through the USB, but through the VIN pin, perhaps with a battery supply. So it definitely needs to go through the onboard 5 volt regulator. But there are some I've seen listed of these that list them as good for 3.3 volts to 5 volts. And they've looked on the line at AliExpress to start with, and they're just saying basically 5 volts. I wouldn't trust them at any lower voltage. If they are listed as being good for 3.3 volts, then they should be good to just run through the USB, because they must be tolerant to a lower voltage than 5 volts. So that's it for this episode. That should be a nice, simple project for students to replicate. Just ensure you use a battery connected to the VI in and ground pins of the nanoboard to ensure accurate results. Till next time, all for now. So if you like that video, hit that like button. If you want to see more, hit that subscribe button. And the notification bell, make sure you get all the videos. And if you're that kind of sharing person, hit that sharing button. For a bit of laziness, if you're not subscribed, look at the arrow, click on that icon, and it'll subscribe you. I haven't even scrolled down or anything like that. Is that it for this outro now? Yeah, I think so. Good.